The first talk, welcome back to the session. Well, it's a session on hard problems. The first talk of the session will be Paolo Santini. Will tell us a little bit more about how to approach the permuted kernel problem from a coding theory perspective. So I look forward to this talk. Paolo, please, the floor is yours.
Okay, thank you, Eduardo, for the introduction. So this talk is about a paper which is going to appear at the ISIT conference this year, and it is a joint work with Professors Baldi and Chiara Luce. And as you can guess from the title, the paper is about a new algorithm to solve the permuted kernel problem. So this is the outline of my presentation. I will start by first defining the problem, and also we will see the state-of-the-art algorithm to solve the PKP. Then we will see the connection between the PKP and the encoding theory. And finally, I will describe to you our idea to solve the problem. So we can start by defining the problem. Well, the permuted kernel problem is a really nice combinatorial problem in which we are given a matrix A and a vector C, and to solve the problem, we want to find a permutation of C that is in the kernel of the given A. To see an example, consider this vector here and this matrix. To solve the problem, we need to find this permutation. So you see that we change the order of the elements in the vector C, so that when we multiply by A transpose, we get the all zeros vector. The problem is known to be NP-hard, and it has been studied since some time ago. And in the slide, I have reported some well-known attacks. And in particular, we will focus a bit on the last attack because it is the state-of-the-art solver. Speaking about cryptography, the PKP has been first used by Shamir in 1989 to design a zero-knowledge identification scheme. Nowadays, the PKP is at the base of PKP DSS, that is a post-quantum signature scheme with really nice features. For instance, very small public keys and also kind of compact signatures. To define the hardest instances for the PKP, we consider these criteria. So we choose matrices that are random and have full rank equal to M. We consider vectors C having no repeated entries, so that the number of possible permutations is maximum. And also we set the parameters so that on average we expect to have just one solution. Let B denote the solution, so the permutation of the given vector C. Consider that basically any attack starts from the consideration that given the initial PKP instance, we can obtain additional information. Consider, for instance, this equation where you see that on the left term of the equations, we have the unknown entries of the vector B, while on the right side of the equation, we have this value which can be computed because it is enough to sum the values of the entries of C. So if we include this additional equation, we obtain what I will call the non-homogeneous version of PKP. That is another problem which is constructed very easily because we just need to append the all ones row to the matrix A, so that in the end what we want to find is a vector B, so that its product by H transpose is equal to S, that has this structure. As I have already told you, the state-of-the-art algorithm to solve the PKP has been proposed 3 years ago by Coussa, Macariora, and Patarin, and I will refer to this algorithm as the KMP because of the KMP is the acronym of the author's initials. The algorithm starts by transforming a given PKP instance into the non-homogeneous version. So you append this row to the matrix A, you construct your target vector. And once you have done this, you apply partial Gaussian elimination. Now, I will not have the time to explain the meaning of all these parameters, but I will leave you the slide so that you can check all of the details. In any case, what's important is that using this transformation, we can write this linear system where we have two main equations. The first equation is referred to the elements that are highlighted in gray, while the second equation is referred to the elements that are highlighted with the light blue. And in particular, you see that if we look at the system, we see that to find a solution for this system, we need to first solve the first equation, and then we use the found vectors B1 and B2 to compute B3. In particular, the first equation defines another non-homogeneous PKP instance. So basically, the procedure of KMP consists in first solving the small instance and then using the found solutions to compute the last equation. To solve the small instance, the KMP algorithm uses a standard uses a standard technique that is a meet-in-the-middle approach. So what you do is that you prepare two lists, L1 and L2, and then you search for collisions. Each list is populated using entries coming from the given vector C. To find collisions, clearly, we use an efficient approach. So, for instance, sorting plus binary search. And once we have the solutions, we use each solution to test B3. The cost of the algorithm has this expression where we sum the sizes of both L1 and L2 together with the number of collisions we produce. Clearly, we have to consider also the number of collisions because every time we find two colliding elements, then we need to test a value for B3. Now, I guess that as I was speaking, you have already seen that the problem has some very strong connections with linear codes. Indeed, the kernel of the given A can be seen as a linear code. In particular, the code is the one that has parity check matrix A and has length M and redundancy M. So starting from this simple consideration, we can translate the PKP into a code word finding problem. The corresponding version, you can see it in the slide. So I give you a linear code C having parity check matrix A. I also give you C. And you, to solve the problem, you need to find a code word B that is a permutation of the given C. Also, we can translate the non-homogeneous PKP into a code-based problem. And to do this, it is enough to define the vector S as a syndrome so that the non-homogeneous PKP basically asks to find a vector B having syndrome equal to S. And clearly, we will focus on the non-homogeneous PKP because it is easier. I mean, we have an additional equation, so we have more constraints on the solution. Solving the non-homogeneous version is somehow easier. Before I present to you our algorithm, we need to understand the role of partial Gaussian elimination. And in particular, its role is fundamental because it allows us to define a small instance having involving few coordinates. Indeed, you can see that when we apply the transformation to the matrix, we obtain this null matrix here. So that to solve the small instance, that is the one highlighted with the gray color, we just need n minus r plus l coordinates. So at a first glance, one may think that choosing L as small as possible is going to make the attack better. Actually, this is not true because we also have to consider that if L is too small, then the small instance has too many solutions, and in the end, the complexity of the attack gets higher. So basically, if we apply simple partial Gaussian elimination, we have this constraint on L so that we cannot play that much with this parameter. However, if we look at the figure, we see that H1 and H2 generate a subcode of the dual code, and this subcode has a small support. So one may think that to improve the attack, we need to focus on subcodes having a small support, because basically H1 and H2 actually define a subcode of the dual code that must have a small support, because a small support means very few coordinates. In the paper, we have this theorem in which we study the average number of subcodes having a desired dimension D and a desired support size W. In particular, what we do is that we can bound such a number. We have found both a lower bound and an upper bound. And in particular, in this talk, we will focus on the lower bound, in the sense that we can consider this rule of thumb, so that if the lower bound is greater or equal than 1, then we expect our random code to contain at least one subcode with the desired properties. So in our attack, we will choose W and D so that this quantity is greater or equal than 1. How can we find subcodes with a small support? Clearly, we use our favorite code-based attack, that is information set decoding. In particular, 2 years ago, Bulens described how we can tweak ISD to find 2-dimensional subcodes with small support. Here, we apply a simple generalization to this technique so that we can find subcodes having whichever dimension D. The attack, the algorithm is very simple because it basically Prange algorithm. So we first apply a permutation, then we use Gaussian elimination to obtain the identity matrix, and then we consider all possible combinations of the rows. If we find a combination yielding a subcode with the desired support size, then we have found our solution. The complexity of the algorithm is described by this formula, and I guess I will not have the time to enter into much details. In any case, you can see that the expression is really essentially analogous to the expression of other ISD algorithms. So we divide the cost of each iteration by the success probability of a single iteration. So we have seen that we can actually find small support subcodes using ISD. And this is the first ingredient of our attack. The second ingredient is how we use such subcodes. So in this slide, I will describe our idea. We start by finding U, that is the generator for a subcode with dimension D and support size W. And then we use this matrix as the matrix defining an initial PKP instance. In particular, this instance, in this instance, only W coordinates of the given vector are considered. We solve this instance using, again, a meet-in-the-middle approach. So we prepare 2 lists, K1 and K2, then we use collision search, and we find an initial set of solutions. These solutions are used to build one of the lists that are used in the KMP algorithm. So you see that we have, again, 2 lists, L1 and L2, but L1 is populated using the vectors we have previously found. We apply collision search again, so that we produce the final set of solutions, and we use these final solutions for the to compute the values for P3. So basically, you can see that the second and the third step are identical to the KMP algorithm. So what we do is applying an initial filtering stage in which we filter solutions using the subcode we have found. In this slide, you can see the running time of the algorithm. And again, I cannot explain all the details, otherwise it will be too boring. But you can see that basically we have, I mean, the analysis is essentially the same that we have for KMP. So we consider the cost of ISD plus the cost of merging and testing solutions. Now, let's see how our attack compares with KMP. In this slide, I have reported an example for the case of Q equal to 251 and considering two values for the code length, 50 and 75. Our algorithm is highlighted with full lines, while for KMP we have used dotted lines. And as you can see, our algorithm seems to be slightly faster than KMP, and in particular, when the rate of the dual code increases, then the gain becomes more important. And we believe this is due to the fact that if the rate of the dual code increases, then the dual code contains subcodes with small support and a larger dimension, so we can actually increase more significantly the performances of the algorithm. To consider a more practical case, let's focus on the instances of PKP DSS. Considering the instance targeting 128 bits of security, we have that the claim cost for KMP is 2 to the 130. Using our algorithm, we can reduce this complexity by more or less 4 bits. If we instead focus on the instance targeting 192 bits of security, we obtain a gain that is a bit larger than 3 bits with respect to KMP, while for the largest instance, that is the one targeting 256 bits of security, we found that our algorithm actually does not improve upon KMP. And we believe this fact is due to the fact that this instance has been designed with a different criterion, in the sense that if you consider the ratio between M and N, you can see that for the 256 instance, this ratio is much smaller than what happens for the other solutions. So basically, in this case, subcodes with small support, it's not that they do not exist, but their parameters are not good enough to improve the algorithm. In any case, if you want to obtain a script computing the complexity, and also if you want to simulate the attack, you can visit this web page where we have published all the code we have used for these results. Now, I am about to conclude, but first of all, I would like to be very clear on what's the meaning of our results. Indeed, one may think that this is an attack on PKP DSS. I mean, the improvement is not dramatic, but still, I have presented running times that are below the security level. Actually, consider that we are neglecting some factors, and also these algorithms have a very large space complexity, so they use a lot of memory. And it is well known that if an algorithm makes use of a large amount of memory, its running time is somehow penalized. Yet, the comparison with KMP is fair, in the sense that the same factors are neglected for KMP. So in the end, PKP DSS probably meets the claimed security level, implying that if you take all of these considerations into account, then the actual running time of the algorithm is above the security level. Yet, for many cases, our algorithm seems to be faster than the state-of-the-art solver for PKP. So, concluding, we have seen that the PKP can actually be studied as a code-based problem, and in particular, we described how we can use subcodes with small support to improve the state-of-the-art attacks. The improvement is not dramatic, but still the algorithm we have obtained is faster than the state-of-the-art for many cases. So I think that one may, well, I believe there can be some room for improvements in the sense that maybe one can improve the attacks using more levels, so merging on more levels, or we can make use of representations. Also, we can use other code-based algorithms, so not only ISD, but maybe something else. I don't know, honestly. I don't know if the answer to these questions is yes or no. And also, one may design an algorithm using less memory. So maybe there is a way to reduce the space complexity of the algorithm. So this concludes my talk. Thank you very much for your attention. And also, I would like to thank the organizers of this really nice workshop. And if you have questions, I will be very happy to try to answer.
Thank you, Paolo. We take questions from this first in line.
Hello, thank you, Paolo, for the talk. I have very basic questions. I didn't understand why you could conclude that the codes, the subcodes, have small support. So for me, it was a bit unclear because I mean we know that there is some to the coordinates we somehow know, but why do they have small support?
I couldn't hear you very well, but I guess you are asking why the subcodes have a small support.
Yes, exactly.
Okay, well, actually, we choose to use subcodes having a small support. So in our attack, we start with this matrix U, and we find U so that the corresponding subcode has a small support. So basically, you can think of U as a matrix having a lot of columns that are full of zeros. And we use this matrix to, well, basically, it's like we are adding another small instance. And if you have a small instance defined by a matrix of this form, clearly to find solutions, you need a smaller amount of coordinates. Okay, so we search for subcodes having this structure.
But then you're building your list from these subcodes. So how can you ensure that your solution is somehow preserved by just looking at these subcodes with small support?
Yes, because we can think of let's think about the homogeneous version. So we are searching for a code word. It's clear that any code word is orthogonal to any subcode. Okay, so any solution to the initial instance is also a solution for the small instance. So this is why using subcodes, we don't filter out solutions. Simply, we focus, I mean, using such a subcode, we find some constraints about the final solution. The constraints are only referred to a small set of the entries, a small subset, but yet using this, we partially create our solution.
I see. Thank you.
Angela?
A simple question for PKP DSS, the 256-bit security, the field was much larger than the other two.
Sorry, but I
will repeat the question. So Angela is commenting on the fact that the high security level of PKP DSS has a much larger field size.
Yes. Okay, so hi, Angela. Yes, so honestly, I don't know why this instance has been designed in this way, because you can see that the defined field size is much larger than what happens with the other instances. And also the value of m is much smaller than n. So it is smaller than n alpha. So probably the reason why our algorithm is not our algorithm does not improve upon KMP is because of these two considerations. So a very large Q and a very small m, a very small, I mean, a smaller m probably makes our attack perform not so good. And I believe that if you choose parameters in this way, then you cannot find subcodes with the desired properties. So the initial filtering, you cannot apply it.
Okay. We have a question from Simona. I don't know if he's able to speak the question or write the question. Simona?
If possible, I will speak.
Yeah.
Can you hear me? Yeah. Okay. So in the end, you have some questions of maybe how to improve the attack, and can we use other code-based algorithms and use less memory? So you said that if you have more memory, that kind of gets penalized, which is normal. But when you think about other code-based algorithms, they make a trade-off, yeah, in the wrong direction. So what would you suggest is a good, maybe something interesting to look at? Because I see kind of like a deadlock here. So what would you suggest?
So I have not a good suggestion. Otherwise, I would have used it. In any case, I can tell you that I tried with more levels and using representations, but I wasn't able to. We weren't able to find a good way to improve the attack. So maybe we are not good enough, or just 2 levels is the optimal point. Going to your question. Well, maybe I think that you can, because the fact is that in these attacks, the running time is basically equal to the size of the list. To reduce memory, maybe you can use, I don't know, maybe you can hope to find a small instance with some properties. So you have like a success probability. Okay, so if you do this, maybe the running time will be kind of the same, but you can reduce the size of the list because you are applying a constraint, which will be satisfied only with some probability.
Right. Yeah, that makes sense. So similar to already the ones that you have, but adding some more. Yeah.
Exactly. Clearly, you cannot use this for sure. So you have some success probability. But if you combine all the factors, then maybe you can have an algorithm which is kind of the same, but requires less memory. But again, I have no idea, really.
So
Yeah. It's interesting to look at, yes.
Just about this topic, I think what
Thanks.
you definitely do to reduce the memory of the algorithm is just use a different matching routine, like not like a meet in the middle matching, but maybe a Schopenhauerian or a section approach to reduce the memory. So of course you're ending up with a time memory trade-off, but then depending on how much we penalize the algorithm, it might get better anyway.
So it's a very interesting topic. I also had a question that I would not ask because we are late, but I can talk to Paolo later. And I suggest, in fact, that you all talk to Paolo and discuss this because definitely I think the topic is very interesting and the PKP problem needs a little bit more scrutiny. I mean, it appears obvious to me. So thanks, Paolo, for the great talk. Really interesting.
Thank you.